Hello everyone. In this video we are going to talk about different types of transformations. Linear transformations, projection, affine transformation, rotation matrix, and similarity transform or similar matrices. So we first start with the rotation matrix. A rotation matrix in general in 3D is a 3x3 matrix that you use to rotate a point with respect to origin or with respect to any specific axis, a specific amount of angle, and get a new point, right? Or you can say that's what you use to describe the orientation of one object with respect to another, or one coordinate frame with respect to another coordinate frame. Rotation matrices are orthonormal matrices, meaning that they're transpose of a rotation matrix and the inverse of a rotation matrix are the same thing, and also the determinant of a rotation matrix is equal to 1 in a right-handed system. We say they belong to a specific group of 3D matrices called special orthogonal matrices, or SO3. So if you ever hear the word SO3, I want you to know that. The other important thing is if you have two rotation matrices multiplied together, like R1 and R2, the result, R3, is going to be another rotation matrix. So the set of rotation matrices is closed with respect to the matrix multiplication. I have two videos, rotation matrices 1 and 2, under my playlist called Robotics. If you want to know a lot more in detail about rotation matrices, you can watch those videos. So here I'm going to talk about them briefly. But a rotation matrix in general is a 3x3 matrix that describes the orientation of the three axes of one frame with respect to another, right? So let's say if you have, if we are dealing with 2D problems, right? So this is my x old, and this is my y old, or x1 and y1, and z old is of course out of the plane toward us. If I go ahead and rotate this coordinate frame and use angle theta, whatever that you want, but counterclockwise, then I will get this set of axis, right? So z new is the same as z old because I'm rotating about z, but this rotation angle, positive counterclockwise, I call it theta. So this is my x new, and this is my y new. So when I describe the orientation of the new frame with respect to old frame, I can use a rotation matrix R, which is of new frame with respect to the old frame. And the way it is each column of this 3x3 matrix describes the orientation of one of the axes of the new frame with respect to all axes of the old frame. In other words, the first column is going to be x new dot product with x old. Okay? So the projection of the new along old, and then again x new dot product with y old, and then again x new dot product with respect to z old. So the first column tells me if I want to write this x new in terms of x old, y old, and z old, how much each component will be, correct? So this describes this new x in terms of all of the old frame axes. And then similarly, if I go to the next column, it's going to be y new in terms of all of the old axes. So y new dot x old, y new dot y old, and y new dot z old. And finally, you have z new dot product again with all three old axes. Okay, so this is how we form a rotation matrix. It has 9 directions, 9 components. Sometimes we also call it direction cosine matrix, because these are all unit vectors that I showed with hat. So when we apply a dot product is magnitude first one, magnitude second one, cosine of angle in between. And since magnitude of all of these x old, x new, y old, and so on is 1, all that this one is giving you is the cosine of the angle between new and old, which is clearly what? Cosine of theta, right? Or y new and x old, the angle between x old and y new, if you look, that's theta plus 90 degrees. So this is going to be cosine of theta plus pi over 2. The angle between z new, which is out of the plane, and x old is simply 90 degrees, right? And so on and so forth. So it's, as you can see, it's just a bunch of cosines. So now x new and y old, that's pi over 2 minus theta, right? That's this angle. Between y new and y old is again theta. Between z new and y old, it is pi over 2, because z new is perpendicular to x old and y old. Between z new and z old, they are on the top of each other, so it's cosine of 0 degrees. Between y new and z old, again, is pi over 2, and similarly between x new and z old, it's also pi over 2, because they are perpendicular to each other. So if you simplify this whole thing, you will get cosine of theta, and then cosine of theta plus pi over 2 is negative sine theta. This is 0, this is 0, this is a 1, 0, 0, sine theta and cosine theta. Okay, so this is the result that you will get, and in terms of rotation matrices, we can call this a rotation matrix about z-axis with angle theta. Okay, so that's what the rotation matrix is. It's a 3 by 3 matrix. If you look, each column is perpendicular to all other columns. The magnitude of each column is 1. If you calculate the determinant using the Sarus's method, you see the determinant is also 1. Okay, so this is a rotation matrix. It describes the orientation of the new frame with respect to old frame, but it does a lot more. Like, for example, if I have a point here in the 3D or 2D space, and this point is called P, well, the coordinate of this P along the old frame is different than what it is along the new frame, right? Because for the old frame, I have to project it perpendicular to the axis of the old frame. So these are the two components that I will get. But for the new frame, I have to project them along the axis of the new frame perpendicular. So I will get this one, and then I have to perpendicular project on the y-axis. So it is going to be this guy here in green, and this one. Look at their magnitudes. But if I do it with old frame, it's going to be this guy in black and this guy in black. Clearly, you see there are different magnitudes, sometimes different signs. So if I want to show this point P with respect to the new frame, and I want to show point P with respect to the old frame, they are different things. Okay, they are different numbers, but can I relate them to each other using this rotation matrix? Absolutely. All I need is to multiply P old by rotation of old with respect to the new. If I do that, I have this rotation matrix. I can multiply it, get the old point, multiply by rotation matrix, and get P in the new frame. Or if I want P in the old frame, and I have P in the new frame, what I need is to multiply it by R of new with respect to old. Okay, so if I want to go back from the new frame, go back to the old frame, see how it was, I multiply by this rotation of new with respect to old, which you have here. So this guy, in this case, this rotation of new with respect to old is r of z and theta that you can see. You might say, what is the new with respect to old? Well, these two are acting opposite of each other. So you can say that r old with respect to new is equal to what? Inverse of r of new with respect to old, because that's what they do. They are doing opposite operation. One goes from frame old to new, one goes from new to old. And since the rotation matrix is orthonormal, the inverse of that is equal to what? The transpose of that. So if I have this rotation matrix that I have here, this is new with respect to old. If I want old with respect to new, all I need is to transpose this guy. So if I want that, it is going to be what in this case? It's going to be 0, 0, 0, 0, 1. This is going to be cosine of theta. This is going to be sine of theta. This is going to be negative sine of theta. And this is going to be cosine of theta. Okay? So it's the transpose. If you apply a transpose, you'll get the other one. Or instead of r of z and theta, you can say this is r of z and negative theta. That's also valid. Because by a rotation z and angle theta, you go from old frame to new frame. By negative theta, you go from new frame to old frame. Okay, so now I want to show you a simple MATLAB demo to understand this better. And what I have here is a rotation z with angle 45 degrees. And I have a point 2 and 3. I want to show you the demo. Just keep in mind that since this demo I'm showing you is only dealing with x and y, and this is a 2D version, I do not care about z, so all I need to focus on is this basically submatrix from 1 to 2 and 1 to 2 of the rotation matrix, because this is what transforms x and y to x and y. The rest of it is for z. Okay, so don't be surprised when you see here I'm only using a 2 by 2, not a 3 by 3 rotation matrix. And when I do that, you get the rotation of 45 degrees, but if you look, the red point is the original point, the green point is the transform point, but if you look at the rotation, it's backwards, right? It is clockwise 45 degrees, not counterclockwise. While here, I used the exact same thing that we mentioned here, and I use 45 degrees, and guess what? I got the rotation backwards. And you might say, well, why is that? Well, I'll tell you why. So this is another case that I'm trying to show you something that might surprise you, but you shouldn't be, because what you did here was you rotated the coordinate and kept the point P the same location. Okay, so the new numbers that you got are the coordinates of the same point P on the rotated frame new. So what you really had here, if I can copy this from here and bring it here and show it to you. So this is your original frame. Okay, this is x old and y old. This is point P. Now you said if I rotate my x old and y old and get the new frame x new and y new, which are what? They are rotated for 45 degrees, so they should be like this. This is one of them, and the other one is like that. So this is x new and this is y new. you said that very same point P, if I project it onto the new axis X and new axis Y, those coordinates that here I'm showing you with bigger line thickness, those are how much? And you found them, and now you are plotting those two numbers that you found with respect to, again, the old frame X and Y. So this guy here that you see, this guy in green, that's the same as that guy in black, and then this portion in green is the same as this small portion in black. So you transform your point, but you are not plotting your point on this new frame. You're again plotting it back on the old frame. So that's kind of not doing it right, basically, right? What you want, if this MATLAB code is not doing exactly what we have been talking about in this lecture, what we let me find it here. What we did in this, what we did here, we kept point P fixed, rotated the frame. What we are doing here in this MATLAB code, we keep the frame the same, we rotate the point. So they are different things. If we want to get meaningful result out of this MATLAB code, we should be doing the exact same thing as this code does. So what we need to be doing is, I kept my frame the same. I do not rotate my frame. I do rotate my point. So I go from point P to P new. And this angle rotation is theta, and I want to see if the coordinate of the original point were px and py, now what are the coordinate of this new point pny and well, not here actually, here, p and x. So we want to find p and x and p and y in terms of px and py, not backwards. And if I want to use the material that I taught you to achieve this, what you can do is this. You say, well, this is what I do. I'm gonna attach a frame to this point P, and I can call it like x1 and y1. And then I rotate it, correct, to get this new one, right? Or maybe I can consider the original frame, but the original frame, I allow it to rotate. I allow it to rotate. So if this is x old and y old, I allow this frame to rotate as much as theta did. So now it comes to somewhere like here. Now, since my frame rotated as much as my point did, the coordinate of this point Pn with respect to the new frame is the same as the coordinate of point P with respect to the old frame. So Pn with respect to the new frame is the same as P old or original P with respect to the old frame. They should have the same coordinates because they have the same orientation, relative orientation. Now the question is this. How can I get P of n with respect to the old frame? Because this is Pn in the new frame, but what I really want is Pn in the old frame. So my question is, what is Pn in the old frame? And you say, well, this is equal to Pn in the new frame, whatever it is, times rotation of the new frame with respect to the old frame. Correct? And for P of n with respect to the new frame, you replace it with what? You replace it with P old. So from these two, you'll get Pn in old is what? Rotation of new with respect to old times P old. But what is this rotation of new with respect to old? If you remember, this is a rotation of z with angle theta. So I get this. So take a look. If I do not rotate my frame, I keep my frame constant, just rotate my point instead. This one says the coordinate of the new point in the same old frame is equal to the rotation z and theta times whatever it was in the old frame. You see? So I should not multiply by transpose as I did. I should multiply by the original rotation matrix. So I should multiply by this really, not this. So when I go back to my MATLAB code, I should make sure this is negative, this is positive. And now if I do it, I should get the right thing. And you can see now the red vector is rotated 45 degrees counterclockwise to get you the green vector. Good. So this is when you do rotation with respect to the same frame. The point does move, not the frame, right? And that's what a rotation matrix does. Now you can change the angle and do, or change the axis and do whatever you want. Okay, so this is the idea of a rotation matrix. Good. Now let's keep moving. And as I said, if you want a lot more detail, watch those two videos I have under the robotics playlist. Now, there is something called a linear map or transformation. What is a linear map? A linear map is when you transform vector x to vector y by simply multiplying it by a matrix. That's all it is. You're not adding anything else, just multiplying it by a matrix A. And this A can represent rotation, as we just saw. It can represent reflection, scaling, shear, and projection. Okay, let me show you other cases. Like, for example, when can I do reflection? Reflection means basically mirror it with respect to some axis, right? So let's say here, if I have a point in the xy frame, if I have some point P, if I say reflected with respect to x-axis, I mean get this new point Pn, which is the mirror image of P with respect to the x-axis. Well, what do I need? If the coordinate of this point is x and y, the coordinate of this is clearly x and negative y. So what should I multiply by point x and y to convert it into what? X and negative y. That's the question, right? To do a reflection with respect to the x-axis. Well, you need to keep x the same, so you need to multiply the first row has to be 1 and 0. So 1 multiplied by x, 0 multiplied by y, that gives you x. The second row should convert y into negative y. So 0 multiplied by x, but negative 1 multiplied by y. So this is going to be what? Reflection or mirror with respect to x-axis. Right? That's all it is. 1, 0, 0, negative 1. Let's do it. So here, 1, 0, 0, negative 1. That should mirror it with respect to the x-axis. And there we go. You can see that. Right? Now, if I want to mirror with respect to the y-axis, the x should be negated. The y should be kept the same. So this should be a mirror with respect to the, or reflection with respect to the y-axis. And that's what you see here. Okay? So that's quite clear what we are doing. So that's a reflection. But there are other things too, like what? Like scaling and shear and projection. What is scaling? Scaling means the magnitude of the vector increases without changing the direction of it. So if this is P, this time Pn is going to be the same as P, but let's say 2 times bigger, 3 times bigger, or 3 times smaller. So all you need is to multiply both x and y with the same factor. So this is going to be like k times x, this is going to be k times y. If k is bigger than 1, you're increasing the size. If it's less than 1, you're shrinking it. Correct? So what do I need? If this is kx and this one is k times y, clearly I need this to be what? I need it to be k and 0, 0, and k. So it's a diagonal matrix with the scaling factor on the diagonal. Correct? That's all it is. So take a look here. I make this like 3003. It should scale it 3 times. And there we go. You can see that, right? No worries. Okay. Now, if I want to scale it down, I use 1/3, right? Or 1/4. So it's going to make it 4 times smaller, right? Look here. There we go. Right? So you clearly see that's the scaling and reflection. What else do we have? We have shear. Shear means you change the angle. Okay? Shear means it's easily visible when you have more than one point. So you have, let's say, an object like this, a point here and a point here, or even you have 4 vectors maybe. So you have like a box. And then what you do to these 4 points, the corner points, you shear the box, so your box would look something like this, for example. Right? So this 90-degree angle is now changing to this angle. So you have this much of shear in the angle. Correct? Or you can do it along the y, or you can do it along both axes. So you can get it, this is a shear along x, you can get it to be a shear along y. So it will be something like this if you do. Or it could be a shear on both axes where it is going to be something like this. Okay, so this is called shear. So in order to visualize shear, you at least need 2 points, not 1. But how do I do shear? If I look at this case in green, shear with respect to the x-axis, the point that was here, let me clean up a little bit. The point that was here, point x and y, now it is changed to a point x prime and y, where x prime is bigger than x. Correct? So if you add a portion of that positive y to that x, that allows your x to grow without your y to grow. So what should I multiply by the original x and y to get the same y back but get a bigger x? And here let's assume they are both positive. So if I multiply 1 and 0, I'll get, 0 and 1 in the bottom row. That guarantees I get the y back. But if I want to get x bigger than original, I multiply by 1 and then here a non-zero number. So let's say if I make it like 1, that means this number is going to be really x plus y. So it's going to be bigger than original x if y is positive. So any non-zero number on the diagonal here, that means grow for x, not y. Okay, so as long as this number is non-zero, that's a shear along x. Exactly opposite of that, if you make this number 0, and this number non-zero, this diagonal, that means you get x back, but y is going to be whatever it was plus a portion of x. So y is going to grow, that's going to be shear along y. And if you make both of them non-zero, then you have both shears, both shear x and shear y. So you need non-zero off-diagonal elements. That allows for a shear. So let's say here, if I make this 1 and 1, I make this a 0.5 and maybe a 0.3. So that means some shear x and some shear y, and they are not even equal. Okay, and as I said, I need more than 1 point. So 1 point of mine is going to be 0 and 3, and the other point is going to be, let's say, 2 and 0. Okay, so I'm going to use 2 points here, and I'm going to allow both points to show themselves, and there we go. So these two in red are the two sides of the original rectangular box, and now if you see, the angle between their transform version is definitely not 90 degrees, and the numbers are changing now, correct? You clearly see that they are not exactly equal. Now, the scaling factor is not big, so you don't see much of a difference here. If you zoom in, you can see the difference a little bit better, right? But if I make these a little bit more, so make this 1.5 and make this off diagonal, let's say 2. Oh, this is 1, this is 2. Now I should see some bigger differences, right? Here we go. Okay, so not only I get shear, I would also get some significant increase in the size of the sides of that box. Okay, so this is called a shear. And now, so I told you scaling, shear, reflection, rotation, and projection. Let me talk about projection. Projection in general, if you want to describe it mathematically, projection, if I show projection by a matrix P, projection by matrix P can be described as P squared equal P. What does it mean? It means if you apply the projection twice, it is the same as if you applied once. Why is that? Well, because if I have this original coordinate and I have a point here, which is x and y, if I say go ahead and project it on the x-axis, well, the projection point is going to be this Pn, which is x and 0. Right? Now, if I apply the projection again on this point Pn and say project it along x again, well, it is already on x. If I project it, my point, if I call it Pn1, my point Pn2 is going to be the same as Pn1 because Pn1 is already on the axis of projection. Right? So if I apply it once or twice, it's not going to affect anything, right? Or 10 times. But 2 is enough to describe it. Right? But that's not the same for rotation. If I rotate this point about the z-axis 45 degrees, it comes here, and I rotate it again 45 degrees, it comes here. So applying the matrix twice or one times makes a big difference, correct? Or if I do reflection, I reflect it with respect to x, it comes here, I reflect it again, it goes back to the original point. Okay, so maybe a reflection about x can be described by p squared equal I, which means if you do it twice, you are doing nothing, right? You know, when you multiply by I, you get the original point back. Of course, that's only with respect to x. Now do it with respect to y. Do you get the same thing? Yes. If you do it with respect to the line x equal y, right? So you bring it back here. If you mirror it back, you get again the original point back. So how can I describe a reflection? Using this. This is a reflection, right? Applying it twice, mirroring it twice, will get the original point back. But p squared equal p is what? That is projection. Now, if I want to really project a point along the x-axis, what do I need? I need to multiply point x and y by something that gives me x and 0. So what do I need? I multiply first row is 1, 0 to get me x back. The next row is 0, 0 to give me 0. So that's all I need. 1, 0, 0, 0, that projects it along the x-axis. So let's go ahead and do that here for you. And I only apply to one number, and let's say that number is 2 and 3. And my matrix, as I said, is 1, 0, 0, 0. And here we go. You see, it projected it right onto the x-axis. Now, if I want to be y-axis, I make this 0, I make this 1, 1. That is projection along the y-axis, as you can see, right? So that is very clear. Now, you might say, what if I want my axis to be arbitrary, right? So I have this to be my frame, x and y. I have my arbitrary point P. And I have my axis like this. I show it with unit vector k, correct? Which has an x component and a y component. If I want to reflect it on that, so get this point Pn. If I say, what is Pn? If P was x and y, what would you say? Well, if I have this unit vector k and this is P, all I need is to what? You know the magnitude of this guy, right? The magnitude of this is the magnitude of P dot product with k, correct? So if I call that magnitude L, L is clearly point P dot k, right? Now that I have that L, and it is along what? Kx and ky, all I need is to multiply this magnitude by the unit vector. So point Pn is going to be that magnitude times the unit vector. So it's going to be P dot k times k. Correct? So this is projection along arbitrary axis. But if I want to do it in terms of the components, P is x and y dot product with kx and ky, then multiply the whole thing by kx and ky. What do I get if I do so? So this is going to be a single number, which is kx times x plus ky times y. And this whole number is multiplied by kx. And this whole number is multiplied by ky. So if I simplify it, it will be what? It's going to be kx squared times x plus kx ky times y. And here is going to be kx ky times y plus ky squared times, this is times x, that is times y. Right? So what matrix do I need? My matrix has to be kx squared, kx ky, ky kx, and ky squared. Multiply that by x and y, that's what you need. So this is your matrix A, general reflection, right? That's all you need. Now, can I write it in terms of k itself? Remember that k itself is kx and ky. Can I write this in terms of that? Yes. If k is written as a column vector, what you need is, this is k times k transpose, right? Because k itself is kx, ky, and k transpose is kx, ky like this. So what you need is k times k transpose. That's what your matrix is. So let's say in here, my K is, let's say I want a projection on line y equal x. You know, line y equal x has cosine d of 45 and sine d of 45, correct? These are the two components of that unit vector. So all I need here for r, I say r is what? K times K transpose, and that's all I need. Look here. Right? If I also draw the line y equal x, you see that is exactly the reflection with respect to that line. Let me show you. Move this out of the way and insert a line for you that goes from 0, 0 to 10, 10, which is line y equal x. Here the x's are not really perfect, but you can see it hopefully here. So this is the reflection. Now you might say that's not perpendicular. It is, but not the way the axes are shown. So this projection here does not look to be perpendicular to that axis, but it is actually if you have the same units for x and y. Right now what I have is the axes are, if you look at the number of pixels allowed for y-axis versus x-axis, my axes are not equal. So let's see if I can apply the command axes equal. It helps. Okay, this is a lot better. And now if I draw my line again, going from here to the corner point 10 and 10, let's see if I can find point 10 and 10, which is here. And now if I draw the perpendicular line for you, you see that's a perfect projection along line x equal y. Okay, so you have to show your axis properly, but that is a projection. So as long as you have the unit vector of that axis k in general, k times k transpose is going to be the reflection matrix. Okay, there we go. So we have the projection also covered. So a simple multiplication by a matrix, depending on how that matrix look like, can give you rotation, reflection, shear, scaling, and projection. You can get all of them from a simple multiplication by a matrix. The only thing it doesn't give you is translation. If you want to move a vector from one point to another without reorienting it, resizing it, or anything, just physically take it from one point, keeping it intact, the same direction, the same size, moving it from one point to another, that's called translation. And that's where you add a simple vector b to your linear relationship. That is a vector of translation. And if you do such a relation between x and y, it's not a linear relation anymore. That is called an affine transformation. I have a video on affine transformation. If you want, go and watch that. I show you all sorts of things about it and animation and so on. But all you need is to add a simple vector to it to show what? To show translation. So here all I need is really, when I multiply it by r, I add a vector b to it, and I have to decide on b. Let's say b is equal to whatever you want. Move it 1 unit x and 1 unit y, and let me get my rotation matrix back to let me get my r matrix or a matrix back to a rotation, if you don't mind. So instead of this, I make it a rotation matrix again, and this time let's say I want to rotate it by 30 degrees. So here we go. Right, so this time I will rotate it by 30 degrees counterclockwise, and I will also translate it. Okay, I forgot this bracket here. There we go. So now if you look, this is my original point. Now I rotated it for, let me make sure I did it right. The only thing is when you do points, it might not show well, but that's okay. Make sure. Do it again. So this is the original point. I should rotate it 30 degrees. It seems that it is rotated negative 30 degrees, and then it is moved to this point here. Okay, so one thing I might do is get rid of the line in green so you can see better. And make sure that I did not make any mistake here. 30 negative. I see. This is sine, this is cosine. Okay, so you have to be quite careful. But there we go now. So now if you look, not only it has rotated 30 degrees, so it comes from that point to this point here. It is also, it's probably somewhere here, 30 degrees. It is also moved 1 unit x and 1 unit y. So first it comes from this red point to this point in black. And then from that point in black, it can be moved to this point in green by a translation of 1 unit and 1 unit. Okay, so this is rotation and translation together. That's an affine transformation. So we covered that one as well. We also said that projection in general is p squared equal p. Now one thing is projection can be orthogonal or oblique. The formula I derived for you, k times k transpose, that was the orthogonal projection. You can also project it oblique, okay? So you don't have to do the projection perfectly perpendicular, right? Here I did my projection perpendicular to that. Sometimes you might project along some specific axis on it and do oblique projection. I'm not going to derive the equation for that, but if you are given the direction, because maybe your axes are not perpendicular to each other, so if you project along the axes on the k, then you might get oblique projections, okay? But again, I'm not going to go over that. I leave it up to you to derive that for yourself. Another important thing is the product of two projection matrices is not necessarily another projection matrix. For rotation matrices, you saw, if I multiply R1 by R2, the result is R3, that's another rotation matrix, which means basically if you rotate a point one time and then do another rotation on the new point to get the second point, the second projected point, what you can do is directly go from first point to the last point by one single rotation, which is the product of those two original ones. Not for projection. If you basically do two separate projection matrices, one x and one y, let's say, and multiply together, the result might not necessarily be another projection matrix. So if P1 is a projection and P2 is a projection, the product of them is not necessarily P3 is going to be a projection matrix. Okay, so just keep that in mind. Finally, the last thing we have is called similarity transform or similar matrices. Two matrices W and Z are called similar. If you can relate W to Z by pre-multiplying it by a matrix like A, the inverse of that, and then post-multiplying it by A itself. So pre-multiply by A inverse, post-multiply by A, that goes from W to Z. then we call them similar. Why do we call them similar? Because they have similar characteristics like eigenvalues, ranks, determinants, and so on. Their components, their entries are going to look different, but not their important characteristic values. Let me show you an example first. So let's say I have W, and W is, for example, 2, 3, 1, and 5. Then I have a matrix A, and this matrix A is, let's say, 2, 6, and then 7, and -3. So now I say Z is equal to A inverse times W times A, correct? And this is Z. Now, if you look at Z and W side by side, they are quite a bit different, right? Not any of their numbers are similar. It's not like if you consider the ratio or the angle of each one of the columns, they are the same, or anything for that matter. So they look completely different things. But now if I run the command eigenvalue on W, it gives you these two numbers, 1.2087 and 579. And if I run it on Z, guess what? I get the same numbers, right? It's just reversed order, but definitely they are the same numbers. And if you look at the eigenvectors, they are the same, of course, as well, right? If you look at the rank of them, of course, the ranks are also what? In this case, both of them should be full rank, right? And so on. So pre and post multiplying by A inverse and A for any arbitrary A is not going to change the characteristics of these matrices, how many independent, linearly independent column they have, and the effect of eigenvalues or anything for that matter, right? Now you might say, okay, what's the use of this? Why should I do that? Well, this is in many cases, especially when that A matrix is a rotation matrix R, that is what we call change of the base, or showing a matrix with respect to one frame, then changing it to show with respect to another frame. Like what? One of the cases is when this matrix W or Z is the inertia matrix. So if this W is the inertia matrix, let's say in 2D case, it is like IXX, IXY, and then YX and YY, correct? These are what you learn in statics or solid mechanics. If you calculate them in one frame, right? So let's say when you say X and Y, you mean the traditional X and Y, and this is your object with area A. So you calculated the moments of area for the frame X and Y. For example, IXX is what? It's the integral of y squared dA, right? And so on and so forth. Then if I rotate my frame and get this new frame, X prime and Y prime, if I say, what is I? So this is I in frame X and Y. If I say now, what is the I matrix or tensor in the frame X prime and Y prime, what would you say? Well, it's very hard to recalculate all of these because now, for example, your I X prime, correct? This is going to be what? Integral of Y prime squared dA, correct? This guy here will be written like this. It has 4 new components for you to recalculate. And guess what? Calculation of these is not really trivial. Okay? So if you want to go from one of these to the other one, the question is, how would you do that? And the answer is by changing the base, by multiplying by the rotation matrix. So if this rotation going from X to X prime is described by the rotation matrix, let's say in this case your R is R of Z and theta, then if I want to show my I X prime Y prime as a function of I, X, and Y, what I need is to use this rotation matrix and I need to what? Use the inverse of that and do pre-multiplication and post-multiplication. So what you really need to multiply here is R inverse and then R. If you have the R, which is not really hard for a simple axis and a simple angle, and get that rotation matrix, apply negative inverse of that and the R itself, and instead of inverse you can also apply the transpose really. That can take you from one frame to, so once you calculate your inertia matrix or inertia tensor in one frame, you can now take it to any other frame as long as the relation between those frames is defined by a rotation matrix. Or if the relation between frames x prime, y prime, x and y is not simply defined by rotation R, but it is defined by matrix A, like this case here, so that A could be a projection, a scaling, or anything for that matter. Of course, you are not going to scale the axis or something, but you might do anything other than rotation. Most of the time, it's just a pure rotation. Then you can, instead of R, you can basically apply what? You can apply A, okay? And it is not going to change the eigenvalues of this inertia matrix, the eigenvectors of them. And you might say, well, what's the importance of eigenvalue or eigenvector of an inertia matrix? If you watch my video on the eigenvalues, you'll see that will tell you the direction of the principal axis, right? So please watch my video on the eigenvalues. And in the second video at the end, you'll see I mentioned the application of eigenvalues. I applied it toward the rotation, toward the stress matrix, which is the same basically as an inertia in terms of what we are doing right now. And you'll see that I used the eigenvalues and eigenvectors, especially eigenvectors of the stress matrix, or in this case inertia matrix, to determine the direction of principal axis. So if they are not changing, the eigenvalues, eigenvectors are not changing, means the principal axis are not changing, which is one of the most important things for solid mechanics. Okay, so this is called the similarity transform, going from W shown in one frame to the similar thing in another frame, the same thing in another frame, as long as the relation between the frames is described by matrix A. So hopefully going through these important topics of linear algebra, linear transformation, affine transformation, projection, shear, all sorts of things, and similarity transformation was useful to you, and I will see you in my next video. Thanks.